Okay, so estimating a population mean. What did we learn? We learned that we are going to use the sample mean, right? We're going to do the sample mean plus or minus the t critical value. And this is what we found, correct? We found this, all right? We know how to do this. We did this. We know how to do this on the calculator, right? What are we using on the calculator? What was it called? It's the T interval test, right? It's a T interval test, okay? T interval test. What was particular about this that we learned? That was, this is the first time we were using a T distribution, right? We talked about a T distribution being somewhat close to a normal distribution with not longer, fatter tails, right? With fatter tails. And we said that the T distribution would approach a normal distribution as the degree of freedom gets larger.
Sure.
Degree of freedom is n minus 1. So actually as n goes larger, as we increase the sample size, the T distribution will look more and more like a normal distribution, right? Okay, good. Very good, very good. So this is what we learned, okay? There were also some requirements. Daniel, what were they? Daniel?
N greater than 30.
Good, that's one. N is greater than 30. What else?
Random sample.
Random sample. So there's random sample. N greater than 30. And there was something else in the middle here. You cannot oversample, right? You cannot oversample. You cannot oversample. You cannot sample more than 10%. Okay? What happens if n is less than 30? What do we do? You would plot it out, right? You would plot it out, and then what are you looking for?
Outliers.
Or?
No outliers.
Okay, you don't want outliers, right? Okay, so that's one thing. What's the other thing?
Normal distribution.
You want something that's roughly symmetrical, right? You don't want a severe skewness, right? Okay, so those are the two things that you're going to do if it's less than 30 and you have to plot it out. Okay, good. So just like when we're doing the proportion, today we're going to talk about estimating this size. In other words, we're going to try, since this is the error, right, we want to, since the error is equal to this guy, okay, we want to, given an error size, we want to be able to control the n, right? We want to find out how many samples we need, how many samples that we have to, how many people do we have to sample, right? So this is kind of different than in the proportions, because in the proportions, this was what? Do you remember what this side was? Not only was this a z, but over here, what did we have?
PQ over n.
Yes, we had square root of PQ over n, correct? Right? Well, that's kind of different with us now because I don't have this. Okay, I don't have this. So the biggest problem now is that when I was doing this for the proportion, right, this was dependent on what? This was dependent on the confidence level, right? Whatever confidence level you were checking, okay? What is this dependent on? Two things. Go back to go look at your table. Look at your table. It was what was the table number? What was the page number? Here it is. 686. So what is this T 1/2 alpha, this guy dependent on? What? the confidence level and the degree of freedom, right? Well, the problem is that the degree of freedom is directly tied to this, which you don't know and you are trying to set. So you're, so you're in a hard place. You don't, in order to find this, you need this, but all I know is this, right? All I know is what the margin of error I want it to be, but these two are interrelated, right? Hence, I don't know what to do, right? So, if you go to page 323, it says that the required sample size is found by using the following formula. The formula is, oh no, what does it say? What critical value are we using? We are no longer using the t interval. The t, because again, they're directly tied with each other. So we're stuck with going back to using just a normal. Okay? So we're just going to punt and say, oh, we'll just use normal one. They're pretty close anyway. Okay? And also, there was a sigma right there. Okay? And 95, 99% of the time, you are not going to know that sigma. That sigma is the population standard deviation, correct? Right? It's the population standard deviation. Okay, here we're using what? We're using the sample standard deviation. Okay? The book says we should use the population one. Problem is, I don't know what that is. So how do we get around that? Let's go ahead and flip the page. Let's go ahead and flip the page. So let's pay close attention to this, okay? Dealing with the unknown sigma when finding the sample size. Okay, number one, use the range rule of thumb. We're going to say sigma is equal to range divided by 4. What's the range? The max minus the min, right? Simply we're going to go max minus min divided by 4 and voila, that's our standard deviation. We're going to call that the standard deviation. Okay, that's one way to do it. Number two, start the collection process without knowing a sigma, and then using the first several values, we're going to wing it. We're going to take the first 100 or so and say, well, okay, this is what I got so far. It must be this. Let's go with this. Okay? So that's number two. Number three, and this is probably the ones that you're going to see the most, says estimate the value of sigma by using the results of some other earlier study. So I'm going to steal, borrow, copy. Well, they did a study that was pretty close to what we're doing, and their sigma was this. So we're just going to use that. Okay? All right? Better than nothing, right? We're going to go with that. So like this one, it says the Wechsler IQ tests are designed so that the standard deviation is 15. Statistics students have a IQ scores within the standard deviation less than 15 because they are more homogeneous group than people randomly selected from the general population. But since we don't have one, and these guys use 15, we'll just use 15. Okay? All right? When determining the sample size n, any errors should always be conservative in the sense that they make the sample size too large instead of too small. In other words, you want to fail on the side of spending too much money than too less, right? Because every time you increase the n, you're spending more money, right? Every time you increase the sample size, you have to make that many more phone calls. You have to email that many more emails or whatever you need to do, right? So they're going to fail on being too big rather than too small. Okay? All right, so let's see if we can do example number 4 and number 5, and then we'll call it a day. Example number 4, assume that we want to estimate the mean IQ score for the population of statistics students. how many statistics students must we randomly select for the IQ test if we want a 95% confidence that the sample is mean is within 3 IQ points? 3 IQ points, which means that what? Which means that this guy here is going to be 3, correct? This guy here is going to be 3. So we're going to use the equation that we have on page 323, where that one involves the z, right? So n is equal to z1 half sigma over e squared. So z was going to be what? 1.96. This guy should be burned in your brain by now, right? This is the normal distribution, half for 95%, right? Sigma, we do not know. We're going to borrow the Wechsler one, which was 15, and we're going to divide this by our 3, right? Because that's what we want it to be. You're going to square it. That's what we're going to do. And if you do that, you get 97 or 96.04. Right? So you want to go high 97, even though it's only 0.04, right? Okay, so 97. That's how you do that. Okay, example number 5. If we know the sigma, then you just plug it right in there, right? Because we just borrowed that one. So use the same 15 birth weights of girls given example number 2, for which the n is equal to 15, and construct a confidence interval with the assuming that sigma is known as 2.9. Okay, so the confidence interval is going to be what? It's this guy right here, right? So this is what? What was our average for that? Example number 2. 30.9 plus or minus, and instead of using t, we're going to use the z, 1.96, sigma of 2.9 with the square root of 15. Does that make sense? Because 15 was the number of the n, right? It was 15. Right? We just go ahead and plug each other that. Right? If you do that, you get 1.4676. So, which means that this is going to be the 29.4 to 29.4 to 32.4. So, we conclude by saying we are 95% confident that the 29.4 captures the true population mean
of girls' weight, of birth weight of girls.
Okay? Are we good? Are we good? You understand that? Okay. It's pretty simple stuff, right? Okay?
Yeah.
All right, so that's that. So what did we learn today? Let's wrap it up. So in finding this, in trying to find this, okay, we had actually used, the equation that we used was this guy instead of the t, right? Right? We're going to use this guy. The question is, how do we get this? The question is, how do we get this? So number 1 was what? What was the first one?
Oh, by range divided by 4.
So you would max minus the min divided by 4. That was number 1. Number 2 was what?
Calculating the sample standard deviation.
Use the first few values.
Use the first few values, right? Use the first, like, well, how many, and then you go ahead and just you say that we're going to call that well the 1. And the other one was
Using something from another
using from
source.
somebody else. So it's beg, borrow, and steal, and we're just going to use that. Okay? All right. Your homework for today is 20 through 28.